Everybody, let's take a look at AP Chemistry Unit 2. We're going to be taking a look at how these elements that we've studied in the last unit and atoms will be combining together to form a chemical bond, and then also hybridization of the electrons found within. So this particular chapter is a lot of conceptual stuff, and we need to revisit a couple of things about the electrons themselves. And the reason we need to do that is because one element will be either giving up electrons or sharing electrons. There's going to be an interaction between different atoms together, and they'll form a chemical bond, a force that holds atoms together. One of the first ways this does it, and probably the easiest way to describe it, is in terms of just a transfer of electrons to produce that stability. We almost always find this with a metal combined with a nonmetal, and so we'll use the example of sodium and chlorine. Now, sodium does have 11 total protons in there, and the chlorine then would have a total of 17 total protons. Now remember I said protons, which means that it's going to have the same number of electrons to start with. So sodium is going to be a 1s2, 2s2, and then 2p6, 3s1. We get to chlorine and we get 1s2, 2s2, 2p6, 3s2, 3p5. And so to achieve that stability of that full octet, sodium would actually be transferring that single electron down into the 3p sublevel for chlorine. And the reason it would do that is the chlorine then would get a full set of orbitals along the way, and then we would get rid of that one lone electron that's in the 3s for sodium. So there's going to be a stability issue or benefit to both of those as we go. Now the result of this then, we would end up that sodium would end up with 10 electrons, and then we'd end up in the chlorine that we would get 18 total electrons. And that's going to come into play a little bit later. But notice that to get this correlation, we only have to move one electron in there. And so my chemical formula would then just be a 1-to-1 ratio. Only one sodium needs to interact with one chlorine in order to get that to go. Okay, so that's the easy part behind that one. And as we take a look at these structures then, we can see that we can do some calculations with this. So when we form a chemical bond with that, we can actually calculate the energy needed to break that bond, and we refer to that as lattice energy. Okay, it's just the strength of that bond in terms of energy. And this is where Coulomb's law does come into play. 2.37 times 10 to the negative 19, that's our constant. And these Q values are going to be representing, remember sodium was a +1, and my chlorine was a -1. Okay, so it's just kind of part of it. Now, the sodium, the +1 part would come into our Q here, and it doesn't really matter which one is written first. I'll just use the cation written first, and the -1 is written here. Now, this r squared represents the radius of each of the ions. Now, remember that if I'm forming the sodium ion in here, this is one of those periodic trends. The sodium element itself, the atom of sodium, is there, but if we lose one electron, he'll get a little bit smaller. My chlorine ion gets a little bit bigger. But since both of those belong to energy level 3, this is kind of a negligent type of factor in there because it's on the same energy level. If there's a difference in it, that would magnify the need actually to reduce the energy involved, because that radius would be much larger in there. But if we find in another example of this, if I was going to move to another example, we just did the sodium and chlorine one. Let's take a look now at my calcium and chlorine. Now, calcium is going to form a +2 ion. Okay, so calcium is going to be a +2 ion, and my chlorine is going to be a -1 ion. Okay, so my multiplier here is a +2 and a -1, and since they're both going to end up, calcium is going to go from the 4s to, it's going to go down to the 3p6 level, going to get rid of those 2 electrons, and then my chlorine is going to go up to a 3p6. It was at a 3p5. So notice that my R value is negligible change as well, because they're both in energy level 3, and so there's no real change there. So I could then surmise that since this is a +1 and a -1, that's 1 times 1. Okay, now here is my 2 times 1, so I could surmise that my calcium chloride is going to have the stronger of the bonds there. Okay, so it's pretty straightforward, that type of math that goes with this. Okay, now let's take a look at covalent, and that's what the majority of this chapter is really all about. If we take a look at covalent bonding, something different is going on here. And so we'll take a look at the example of water, and I'm going to do the orbital diagrams for water here. So my hydrogen is going to be here. I'll just put my oxygen here so we can see a side-by-side comparison, and we'll put our second hydrogen down here. Again, I'm just doing this for the sake of just visualizing what's happening at these orbitals. So here's my 1s2, here's my 2s2, and then it starts at the 2p is where things get interesting. Okay, so we're going to see 1, 2, 3, and then with my oxygen, we're going to have 1, 2, 3, and 4 electrons. Now, hydrogen has only 1 electron right here. And so what's going to happen is one of these is going to go here, and the other one is going to go here. But it doesn't just stay there. What ends up happening then is to make this 1s also compliant, this electron is also going to at times go back over here, and this electron is going to go also here. So it's not just totally giving it up, they are sharing them back and forth to produce that stability. Okay, so that's what's going on just visually within those compounds of water. Now, electronegativity can actually dictate how much they're going to be what we call a percent of ionic character, how much they're going to be giving up or sharing those electrons back and forth. We did talk about electronegativity within the last chapter of just the periodic trends with it. And so the ability to attract those valence electrons, how much they like to take the electron in, is calculated out by a percent ionic character. So we can use this chart to figure out what if it's going to be ionic, if it's going to be covalent, and even within that something called polar and nonpolar. And so here's your equation with this, and we need to derive this just a little bit when I take a look at using this equation to figure out if something's going to be ionic or covalent in nature. Now, first of all, with this we just have to understand a couple things. Always use the bigger number here, the bigger value. And you're going to see a reference table come up in just a second, so you'll know what I'm talking about. Always use your bigger value here, and then we'll use our smaller value for that electronegativity here. And so then we divide it by the big number again, and then don't forget to multiply it by 100%. Now, I mentioned that there's going to be a table that we're going to reference, a reference chart with that, and that's what we refer to as Pauling's electronegativity. This will always be given to you, or the values will be supplied for you. So if we take a look at the example 3 with this, let's take a look at what water would be, and we can calculate then what is going to happen. Is it going to share, or is it going to just donate up? So let's take a look again at example 3. Let's take a look at that relationship, that bond between the hydrogen and the oxygen. Well, here's my oxygen, and here's my value for my hydrogen. Okay, so if I have the difference, my big number is going to be a 3.5 minus my 2.1. And I'm going to subtract that or divide that from the 3.5. We're going to multiply that then by 100%, and we're going to roughly get 40% ionic character. Okay, so what that means is your oxygen is going to pull the electrons 40% more than hydrogen, but that's not enough to keep it overall. Okay, so my oxygen is going to have a 40% influence over that, but it's not enough to keep it forever, so it's going to send the electron back to the hydrogen as well, and so the electron spends more time with oxygen, so it would be polar then. Okay, if we take a look at some other examples with that, we could see, for example, my oxygen. Okay, oxygen would be, and oxygen gas, I should say, is a 3.5 divided by minus a 3.5 divided by a 3.5, because it's the same thing all around. And so we're seeing that it's a 0% ionic character. Okay, so that means that it is definitely a covalent bond, and it is shared equally, and that would be non-polar in there. Now, how I know those polar and non-polar along the way is simply by looking at these different values. Okay, let's take a look at an example of sodium chloride then. Okay, sodium chloride, remember that's what we did already. We take a look at this value and I see, okay, we've got a 0.9 and we've got ourselves a 3. So 3 minus a 0.9 divided by 3 times 100%. And so that would give me a 70% ionic character. That is definitely within the ionic realm. So we say that the electron is 100% of the time, or I should say 70% of the time, are going to be just kept over with that other one. Let's take a look at the example of sodium and sulfur and sodium sulfide. So we see a difference, 2.5 minus a 0.9, and we divide that by 2.5 times 100%, and I get 64%. And so we would then again say that sodium sulfide would be an ionic bond. Now remember, there's a cheat to this because I saw sodium is a metal. Everything over on this side is a metal. So we would say, yep, definitely. I could just look at it, but I could prove it mathematically just by doing the Pauling calculations there. All right, so the rest of this chapter is really going to be focusing on this covalent bonding. Okay, it was first suggested by the physical chemist of Lewis. Now remember, we did do a quick introduction. If I was going to do, say for example, my chlorine, 1s2, 2s2, 2p6, 3s2, 3p5. All right, you'll recognize this name of Lewis because the Lewis dot diagrams came out of his observations here. I describe it in class. If we're looking at chlorine, I describe it in class. The dot diagram is simply the S's and P's of the highest energy level. Those are the ones involved. The other ones are shielded in there. So I see two S's, two S electrons, and then I have five, which is 1, 2, 3, 4, 5 dots, 5 electrons, and we saw that correlate with the orbital diagrams. Okay, so that's where Lewis came up with all of these things and suggested that non-metal atoms, by sharing the electrons back and forth to form that pair bond, can acquire a stable noble gas structure. Okay, so the rest of this is just getting used to and envisioning how these bonds are going to be formed. So at this point, we're seeing some terms. Those electrons, again, if I go back to what I wrote out with chlorine, for example, the S's and P's of the highest energy level, those would all be valence electrons. Okay, valence electrons are electrons of the outermost energy level, the principal energy level. The Lewis structure then would be that model. Okay, this is the Lewis structure for chlorine. The model of that covalent bond, and we have bonding pairs of electrons. When I said that they're being shared back and forth, those would be what we call bonding pairs of electrons. And then sometimes there are extra electrons around that atom, and we refer to those as unshared pairs, non-bonding electron pairs. Okay, so just got to get used to those terms because all of these things will be then telling us what shape these are going to be forming when they form a compound. So here's the game of the whole thing. First of all, you want to add up all the valence electrons that are involved in the molecule. Then we want to pair electrons first to form a bond, and then we're going to be adding the extra ones, all the other electrons, to satisfy the octet rule. So we're going to be seeing these in action. Let's take a look at 4 different compounds of how we can form a bond and envision the Lewis structure for these. So now, first of all, we have hydrogen that has 1 electron, and we're going to add that to another hydrogen that's 1 electron, and we have oxygen, the valence, we would have 6 electrons, valence electrons there. So that's 8 total electrons we have to account for. Okay, 8 total electrons. So we draw our elements, we write out our elements, I should say, and we're going to form a bond between them, a shared pair of electrons first. Okay, so that takes care of 2 and 4. I have 4 more electrons to account for, don't I? And so what we'll need to do is we'll need to take a look and try to satisfy the octet. Now notice I also say or duet. Hydrogen itself is an energy level 1. It doesn't need any more than 2 electrons because energy level 1 can only hold 2 electrons total. So hydrogen is full. We have 4 more electrons, and so the only place that they could go is in unshared pairs around that hydrogen. That is the valence, the Lewis structure for water then. Notice that we've got 1 shared pair here, 1 shared pair here, and then 2 unshared pairs on top and bottom of my oxygen. Okay, now let's take a look at carbon dioxide, a little bit different. I have my carbon, I have my oxygens, and carbon has 4 total electrons, valence electrons. My oxygen has 6 electrons, and my other oxygen has 6 electrons. Okay, so valence electrons are the important part. I have 16 total valence electrons to account for. So let's form a shared pair first. 1, 2, 3, 4. Okay, now, outermost elements will need to get their electrons first. So let's take care of the octet rule around oxygen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so we had 2, 4, 6, 8, 10, 12, 14, and 16 total electrons. But you notice we've got a problem. This inner carbon right here is lacking that octet rule. So what's going to happen is we're going to have to move that pair inside and this pair inside. And we're going to have to form what's called a double bond. So ultimately what you can do is just move those electrons to the inside, and notice that these two oxygens on the outside are going to have electrons unshared on the outside. Okay. Now, ultimately, if I was going to translate this, those dots that I have here, if I transform it into lines to represent a shared pair of electrons, and we would see that we have a double bond on both sides. This represents my 16 total electrons. And don't get too worried. You saw me change from oxygens on the top and bottom to the sides and so on. Don't worry about those things. That's just fine as we go. Now let's take a look at my cyanide, which is going to be my Cn with a negative charge. So this is a polyatomic ion, and carbon, again, has 4 valence electrons, and my nitrogen now actually has 5 total electrons. Okay, but it does have an extra electron to account for here. So I see 9 electrons on the elements themselves, and I'm going to have 1 more total electron just added in because it is a polyatomic ion. So I take a look at my carbon, I take a look at my nitrogen. Let's do a double, a shared pair in between. Okay, so that's 1 and 2. Now I have a total of 10 electron to account for it all. Okay, so carbon, we have 2, 4, 6, 8, and 10. Uh-oh, we've got an issue, don't we? We see that we've got carbon is completely full, but nothing on the nitrogen side. Well, what if we were to take that pair here and that pair here? And so carbon still is satisfied, but look at what nitrogen ends up with. Nitrogen has 2, 4, and 6. Here's 8, and we have 2 more overall on the nitrogen side. Okay, so we see we have 10 total electrons, and so the last electron is going to be on the outside of that compound, just signifying that we actually had 1 extra electron, because if I just add up my valence electrons, I have 9 total within the compound. We have 1 extra electron that's accounted for with my nitrogen on the outside. All right, so let's do this last one between carbons and hydrogens. Okay, and it's going to form actually a catenation on this one because I have 2 carbons and 6 hydrogens. So it's a complex molecule. Use the word catenation. Catenations are chains. And so we're going to see that my carbons are going to end up forming a chain. And remember, I have carbon with 4 total valence electrons. We have another carbon of 4, and I have my hydrogen with 1. I have a hydrogen with 1. And so again, we're going to keep on going. We're going to have 6 total electrons there, plus 4 is 10, and 14 total electrons to account for. So let's combine my carbons together first. And then on the outside then, we're going to be forming my hydrogens. Okay, so we want to make sure we distribute those out. And we've got 6 total hydrogens to account for. So we've got a compound here, we've got a bond here, a bond here. We're going to form a bond between those ones and those ones and those ones. Now the reason I put my hydrogens on the outside is because, remember, only 2 electrons can go there. So you can't combine your hydrogens together. They would go floating off because they have their own octet or duet for that case. So let's count up how many electrons we've actually drawn in just to form our first covalent bonds. We have 2, 4, 6, 8, 10, 12, and 14. And what do you know? We're already done because I have my 14 electrons accounted for. Okay, so we just have some basic fundamentals with valence electrons forming those Lewis structures. Now, with that, notice that I drew those out, and you might wonder, well, wait a minute, isn't there another way to draw it? Simpler way to describe, that would be a simpler way to describe resonance forms. Resonance forms are ones that essentially have a couple of different options in there. Sometimes the bonds and molecules will be alternating between single and double bonds. Sometimes they're just going to be different or alternate forms. Okay, we refer to those as resonance structures. Okay, so let's take a look at resonance structures of these compounds. Let's take a look first of all at sulfur dioxide. Okay, SO2. Now, first of all, remember sulfur and oxygen all have 6 valence electrons. Okay, so we have essentially 6 times 3, so we have 18 total electrons to account for. And so we're going to put, since there's only one sulfur, we'll put that in the middle. We have my oxygen here, and we have oxygen here. 18 total electrons, so we have 2, 4, 6, 8, 10, 12, 14, and 16. And so we're going to have another pair here. Now, notice my sulfur doesn't have a full octet. What do? We share 1 over in this right here. And so essentially we end up with oxygens. One of them have a single bond, and the other one is going to form a double bond. Okay? And that takes care of all the electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. Done. Now, if this is the first oxygen, this is my second oxygen. Notice that we have a double bond with my second oxygen. But nothing says that it had to be these electrons that moved. Perhaps it was from this one. And so even though it seems kind of cheating, really what could happen is my other oxygen could be doing that double bond as well. Okay, it doesn't matter if these lone pairs are on top or bottom, but do know that if I was going to look at this, my first oxygen might have that one that is a double bond instead of my second. Okay, now let's take a look at the next example, which would be nitrate, NO3. Okay, now nitrogen, again, has 5 total valence electrons, and we have 3 of the oxygens that have 6. So 3 times 6 is 18. And so we have plus my 5, that's 23, but notice I have 1 more electron to account for, so that's going to be 24 total electrons. Okay, now let's put this nitrogen in the middle. Let's put that with my oxygen. We're going to do that with another oxygen, and I'll just put my third oxygen down here. So that's 2, 4, 6, and I have 18 more electrons to account for, don't I? Okay, on the outside is going to be that pair, that lone electron. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Oops, this nitrogen, he's going to be missing 1 set of electrons, but we can't add any more because we've already hit my 18, so I'm going to maybe move those in. Now remember, this whole thing has 1 electron on the outside. So that's one of the possible structures of a resonant form, but maybe this oxygen has the double bond. Maybe this oxygen has the double bond. So there's nothing that says which specific oxygen has to have that. So we might have oxygen 1 has the double bond, and that would leave me with 2 electrons, 2 lone pairs of electrons here. This oxygen would have all the lone pairs out here. And so we would just rotate them between this oxygen or this oxygen or this oxygen. Those would all be examples of resonant compounds, okay, resonant structures. Let's take a look at the last one, and this involves my carbon with my oxygen and my chlorines, okay? Carbon has 4 valence electrons, my oxygen has 6 electrons, and my chlorine has 7, and we have 1 more chlorine in there, so that's a total of 24 total electrons to account for. Okay, 24 total chlorine electrons to account for. So let's take a look. We'll combine up my chlorine. We've got to include an oxygen in there, and we've got to include another chlorine. I could have put it over here. Who cares? That doesn't matter. Don't worry about those. So we have 2, 4, 6. And so I have 18 total electrons yet to fill in. 2, 4, 6, 8, 10, 12, 14, 16, 18. And once again, oops, this particular carbon needs to have 1 more set of electrons, so let's share 2 more down here. So essentially, to form this compound, I might have my oxygen have the double bond right here. Now, you might ask, well, wait a minute, so what about this. So notice we have 2, 4, 6, 8. Sorry, I shouldn't have included those in there because they moved, didn't they? 2, 4, 6, 8. Okay, so that's basically how that would work. Now, we can't find any other structures than this. I know it seems like I just moved those things in there, but here's one thing about chlorine. Remember, he only wanted one electron shared in there. So there is a rule in there that you can never, ever, ever get a double bond onto a chlorine. I showed it to you with oxygen, but we're not going to see that those are going to be moving up in there. It's just one of those rules of chlorine because it only had one electron to gain to get that full sublevel. It will never do a double bond, so there is no resonance structures within the carbon, oxygen, and chlorine compound. Okay, that's just one of those things to keep in mind as we move forward with this chapter. Now, those resonant forms, okay, what we're achieving with that. This doesn't tell me necessarily that we don't want to imply that different kinds of molecules with electrons shift forever between them. There's only two types. There's only one type of sulfur dioxide molecule. Its structure is the intermediate between those the resonant forms of the sulfur dioxide in there. We can anticipate when it's possible to write two or more Lewis structures that they're about equally plausible. There is no right answer with this. In the case of the nitrate ion, there are three structures that are equivalent. One could then write many other structures, but as long as we got the octet, we really couldn't achieve that. Resonant forms then differ only in the distribution of the electrons, not in the arrangement of the atoms. So you can't just rearrange the compound and put one on the inside. That doesn't constitute a resonant form. We got to keep the same format for it. It's just where those electrons will be shifting around. Okay? So what I mean by that is that we can't just automatically shift the order of A, B, C is what it's normally doing here. We just can't arbitrarily shift the compound to something completely different. It's not even the same compound anymore. That's all I'm saying with that example of it. Okay, so just kind of watch some of those fundamentals as we go. Now, that should take us through some of the different examples of this. Now, formal charge will be a part of section 2, and so really we should be able to do problems 1 through 3 on there, drawing out those different ones, and we should be in pretty good shape. Good luck to you.